Okay, good morning. Introduction to Systems Engineering. This is a day and a half to 2-day course that we run regularly on scheduled public courses and on site if necessary. If there's a quorum of people on your organization would like to have a training course and minimize travel costs, we do this on site as well. So I'm going to kick off. Just a bit of an introduction to me, Mark Williamson. My background is I did 23 years in the RAF, avionics, and a software engineer. And for the last 17, almost 18 years now, I've been with SyntheSys and now managing director of SyntheSys Technologies. And I am really fundamentally responsible for system engineering training course delivery, apart from trying to run the business. Training course delivery, the introduction to systems engineering, which we're going to touch on this morning, including requirements writing training, and also as we've got a session this afternoon as well, in COSI systems engineering certification preparation training. So helping people, giving people the enablement to pass the certification exam for ASEP and CSEP. I don't know if anyone is in that session this afternoon, but we'll be covering that at 2 o'clock. And I also do systems engineering consultancy and support our IBM business as well. So that's basically me. SyntheSys, we've been around for quite a while now, founded in 1987. Based up in Whitby, the wonderful Whitby on the North Yorkshire coast. And we also now have a satellite office and meeting rooms in Gateshead as well, should that be more applicable for any meetings, training courses or sessions. So the agenda for this little session, this is, I'm going to try and attempt to cover the core of the material that we do over the 2 days. So we'll start off with what is system engineering, and you might wonder, well, that's a bit of an obvious question, isn't it? But you might be surprised as to the definitions some people might have for system engineering, and quite often we get the question, well, I don't even know what system engineering is. So we're going to touch on that, a few definitions of that, and then the key principles of system engineering. Around requirements management, verification, validation, etc. System engineering is largely process driven as well. Well, that is if you do it correctly. So we're going to touch on the process identified within the ISO 15288 2015. We're not going to be glad to know we're not going to go through all of those because that would take about 3 days. And then touch on the life cycle. What do you mean by the life cycle? And then finish off with a little bit about requirements, fundamentals, and what constitutes a good requirement, effectively. And then, as I said, Q&A at the end. Please feel to drop anything in the Q&A, and we'll address those at the end. I would say though, when I do deliver these training courses, we tend to do questions as we go along because when it's pertinent, people will pop up. But for the benefit of this webinar, please just drop them in the chat and we'll pick them up at the end. Okay. So what is system engineering? A few poignant definitions, and these are all actually defined within the INCOSI handbook. And the INCOSI handbook is the reference, the system engineering handbook is a reference for all of our training material, whether it's the requirements, the foundation course or the CSEP preparation. So I've put this in bold, an interdisciplinary approach. Okay, so it requires interdisciplinary approach. You might have mechanical engineers, you might have requirement engineers, you might have test engineers, you might have chemical systems. So an interdisciplinary approach, and it means to enable the realization of successful systems. So that's just a wordy way of saying, building things correctly, building complex systems. And system of systems as well. So, another one, and of ISO 15288, as I mentioned, a formal mechanism for development of a product by a supplier for delivery to an acquirer. And those are sort of terms that are embedded within the system engineering handbook. And quite often, in reality, an organization will acquire some materials and then integrate those or develop those to supply another product. So a formal mechanism for development of a product, and that formal mechanism is further enhanced by the use of these technical processes that we're going to cover a little bit, identify a little bit later. So wrap all that up, development of a product or a system. So quite useful to identify what we mean by a product or a system, or even a system of systems in that multidisciplinary environment, with the controls and processes to make sure that we can produce a quality product and ultimately meets the customer's needs, or what we call the stakeholders' needs. And there's a considerable amount of derivation from needs and wants into stakeholder requirements, and then into system requirements, and then into design as we flow through the system engineering process. And ideally, we want to think of the holistic approach, how we can concentrate the design application of the whole system rather than individual parts. So this is more and more becoming relevant these days with systems thinking, trying to consider how the system's going to operate as a whole, and how other system elements will interface together to provide the holistic solution. So the system of systems, if you like. So we're wanting to consider the whole system rather than stovepiping ourselves into individual parts or system elements. So this lovely slide here, I hope everybody can see that okay on the screen, is the technical processes that identified within the 15288 standard and the System Engineering Handbook. So we don't cover all of these in the Introduction to System Engineering course. We do cover all of them in the SEP preparation course, because that's the benefit, the purpose of the examination. So, but just I'm going to walk through these. They don't necessarily flow in any particular sequence. However, there's a bit of a thread here, really. So we start off, we've got 4 pillars of processes: the technical processes, the technical management processes, the agreement processes, and the organizational project enabling processes. And they're almost like a different multi-level, if you like. So the technical process, this is at the front end. This is actually doing the good stuff and the engineering. So we really start off at the beginning of the process, at the beginning of the life cycle, with business and mission analysis process. And this is really all about those needs and wants I mentioned earlier on. So nothing formal, not any particular structure and requirements definition, but identifying what the opportunity is, or what the gap in capability is that may trigger a system engineering project or system development. Once we've got those needs and wants identified, and they can come from marketing, that come from sales, can come from the technical team that just identify, oh, this manufacturer's got a capability that we haven't got. That's a gap in the market for us, or we need to fill that. So that's where business and mission analysis comes in. Once we've got those, we flow those into stakeholder needs and requirements definition. And that really is the first level of requirements, proper requirements definition, writing requirements in a structured way. And we'll touch on that a little bit later. Once we've got the stakeholder requirements identified, we then derive those into system requirements. So we're transforming that stakeholder user-orientated requirement definition and deriving it into the first repetition of a system definition. So the terminology would be the system shall rather than the user or stakeholder shall. So once that's all done, configured, baselined, and under change management, then when we take those system requirements and then we do some architecture definition, perhaps. And that largely depends on the complexity of the system. Sometimes it's not required. In a lot of cases, it will be required to actually analyze those system requirements and come up with a number of candidate architectures that will all meet those system requirements, but will have some different parameters, maybe for low risk, low cost, high risk, high cost. So you have some options to determine what the architecture is going to be. So, and this is where things like MBSC is really useful for modeling and for identifying, confirming requirements early in the life cycle. So once we've selected one of the architecture definitions, then we go into design. And this is the first point where we actually start determining how the system is going to do it rather than what the system is going to do. So system analysis process can be incurred or at any point in the life cycle. It doesn't happen in any particular sequence. Anywhere we need to make a decision about something. So which architecture we're going to select, maybe trading off requirements, for example, analyze the requirements and determine which ones can be traded or tailored. So system analysis process at any point in the life cycle. Implementation then is implementation of a specific system element, not the whole system as a whole, just a system element. And then once we've got these system elements produced or implemented, then we can integrate them in the integration process. And we go into the integration process, lots of different methods for that, top down, bottom up, big bang approach. There's multiple ways of doing integration. So we touch on those. Verification and validation processes, always a good opportunity for a good argument, I think. Verification, validation. Verification, are we building the product right? And validation, are we building the right product? So as we're working our way down the V diagram, and we're going to come to that in a few minutes, are we actually deriving the requirements correctly? Are we actually building what the stakeholder actually originally asked for rather than something completely different? So verification and validation, and they're sort of parallel activities that occur right across the life cycle, really. The transition process is a process that determines how that developed system is then handed over or deployed in its place of operation. So transition process. Operation process, fairly obvious, really. This is just the operation of that system in its intended environment over its intended life cycle. Okay. And once it's in operation and in use, the system will inevitably need maintenance. It may well need midlife updates. It might need enhancements. It might need defect repairing. So that's the maintenance process. And finally, we have to think, how do we dispose of this process? So this is an area that very often is not considered. And the disposal process, we can't worry about how we're going to dispose of it at the end of the life cycle. We need to consider that really early in the life cycle and have a concept of disposal right at the very beginning, so we can design that into the product and how we're going to dispose of that. So that's the technical processes, and that's the cool face stuff, actually doing the good old the engineering. And really poignant to note that of all of those 14 processes, there's 3 just on requirements. So the importance of getting requirements correctly, and I'm sure there's a few on this call today that have been in this area for a while, but getting those requirements elicited, get them captured, getting them recorded, getting them managed, managing the traceability is absolutely key to successful system engineering system development. Then we go to the technical management processes. So we've got project planning. And this is project planning with regards to the system engineering effort rather than project planning from a project management type of point of view. And the primary output of the project planning process is the system engineering management plan, along with work breakdown structures, etc. So project planning process is the first one, and it fairly obvious again. It should be done as early as possible in the life cycle. It also determines what system engineering processes for the system engineering management plan. It also determines which process you're going to use, which activities are going to be pertinent to this particular system, and we call that tailoring, when we tailor the process accordingly for the complexity of the system that we're developing. Once the project's up and running, we need to assess and control it. We need to manage it. We need to monitor it. We need to take lots of measurements. And there is a measurement process in this pillar as well to determine how we take our measurements, how we take our metrics, and how we feed those back into lessons learned and the improvement of our system engineering processes. Decision management process, fundamental to determining how we move through the life cycle. So we're going to look at this in a few minutes, but we have a concept of stage gates or decision gates as we go through the life cycle. And every time we need to make a decision, there has to be a documented process on how we do that, and make sure we make that decision in a consistent way against the life cycle aspects of business, budget, and technical. Risk management process, as always. Risk management process handles how we consider the likelihood of something going wrong, and if it does go wrong, what's the impact of that happening? So risk management process looks after that. And then configuration management process, what I sometimes call a necessary evil, because it really is sometimes gets in the way of just getting on and doing the job, but it's fundamentally critical that configuration management is done well. So the whole concept of identifying what your configuration items are, making sure you can audit those, making sure you can have a configuration change board, all of that is built into the configuration management process. And the consequences, as I'm sure you're aware of someone working off the wrong document or the wrong drawing or the wrong specification is really disastrous in a typical system engineering process, and can quite often trigger a significant amount of rework. So you might imagine we've got all these processes going along. We've got lots of information being developed. We've got lots of measurements. We've got plans. We've got verification criteria. We've got requirements. We need to manage that information in a certain way. So the information management process is all about how we manage that information, how we record it, how it's stored, how it's retained, how it's made available. So that's information management process. And then the measurement process I touched on earlier. So a means of taking metrics of our system engineering activities and using those to constantly improve our system engineering processes. And then finally, on this pillar, the quality assurance process, as opposed to the quality management process, which is more at an organizational level, the quality assurance process is all about ensuring that as we're developing the system, we're doing it in accordance with the organizational quality management requirements for ISO 9001 or whatever quality standard you happen to be working with. So, agreement processes are two sides of the same coin, really, acquisition and supply. And if you recall, when we go back to that earlier definition of system engineering, of all about realizing successful systems by acquiring and supplying. So acquisition process, how we go about acquiring materials, going out to tender, ITTs, requests for proposals, things like that. And the supply process, actually providing that service or that system element or that component into the system development process. That's agreement processes. And then finally, organizational project learning process. So another level, a level up here. So we're thinking at your organization, at your business level, what do we need to have in place to conduct system engineering activities? So life cycle model management process, which life cycles are we going to have available? Are we going to use sort of and we'll touch again this a little bit later, plan-driven, sequential, agile, lean, and we have a number of life cycle processes, and this is all about establishing for your business model what type of life cycles are going to be applicable to the types of systems you're going to be developing. Infrastructure management process then is all about bricks and mortar. What facilities you need, what labs you need, what test facilities do you need, what basically bricks and mortar infrastructure you need to deliver system engineering activities. Portfolio management process is a little bit of a strange one, this, I think, because portfolio management process is all about, from a chief financial officer type perspective, understanding what contracts your organization will have in the pipeline that can deliver the level of revenue or reputation or products to meet the business needs of your organization. So it's a contract selection mechanism, if you like, to determine how we deliver against your organizational goals. And human resource management, fairly straightforward, having the right people with the right skills at the right time. So managing resources, human resources between different projects within your organization, and making sure everybody's got the right skills that they need to deliver against the organizational goals. Quality management process, making sure that your organization can meet its ISO 9001 or whatever quality standard you happen to be using audit. And so making sure all of the boxes are ticked and assessments are carried out. And last, but very definitely not least, is the knowledge management process. So the risk of having all the information and all the good knowledge in one person's head to an organization is extremely high. So when Bill knows everything about everything and he can fix anything and he can answer all the questions, but then he doesn't decide to come into work next Monday, that's a significant risk to your organization. So having a knowledge management process where your processes and your procedures and activities and your organizational structure are all captured and available for people to see is really, really useful, and mitigates against the risk of those key people not being available for whatever reason happen to be, whether they win the lottery on a weekend or whether they decide they'd rather go and tour Europe and climb some mountains. So it's a big risk to the business. So that's the processes within the INCOSE handbook and the IEEE 15288. Again, to say, on the Introduction to System Engineering course that we're discussing here, we take a superficial look at this, and we look at some of the key ones around verification, validation, and the stakeholder requirements, etc. But we don't go into all of these over the space of a couple of days. Okay. So the V model. Very simple representation of the V model. I'm sure everyone has seen multiple versions of this. However, this is about as simple as I could make it, really, just to explain the concept of starting at the top left hand of this V and working our way down from stakeholder requirements, deriving into system requirements, then deriving that into architecture, and then into subsystem requirements or system elements, and finally down to implementation at the bottom. And as I mentioned earlier, as we're doing all of that, as we're working our way down the V through the life cycle, we are validating. Are we building the right product? So as long as our requirements flow down and are derived correctly and satisfy the level above, then we will provide a level of validation that we're actually building the right thing at the end of the day. And as we work our way up the right-hand side of the V, we're doing verification at the various levels, subsystem, integration, system tests, operational tests. Now, this V can be as compressed or as extended as it needs to be for the complexity of the system you're developing. So again, as I say, I've made this particularly simplified because it just identifies the concept of working our way down the V. And you may well be familiar with other concepts of like waterfall, for example, which was largely used in software development sort of 10 or 20 years ago. But that sort of required the waterfall approach, where one element had to be completed for the next one, and then it had to be completed for the next section. Where so this has a much more of an iterative process where there will be looping between system requirements. You may well define in the system requirements you need to go back and do some stakeholder requirements again, and that would require a change request. All right, to make those changes. So V model, absolutely the fundamental pillar of system engineering. As I say, there are other methods. There's a W model and spiral model, etc. But V model is the fundamental way of doing system engineering as a framework, as a mechanism. Okay, let's establishing the life cycle. So I've mentioned the life cycle. What do we mean by the life cycle? Well, a life cycle is a framework for the development of the system, and we tend to break that into stages, or life cycle stages. And the generic life cycle from within the System Engineering Handbook is a concept into development, into production, into utilization and support, and finally retirement. So we need to have a framework for developing our system through stages, if you like, life cycle stages. So each of those stages will be, you will progress from one stage to the next, usually with some sort of a decision gate or a stage gate, you might want to call them. So a stage gate will determine whether you're happy with the particular artifact or document, may it be stakeholder requirement or system requirement or architectural design or test procedure or whatever. The decision gate will then determine, are we happy with that? Are we happy to progress with that? Or do we need to go back and stay where we are, or need to do some rework? Or do we need to even go back to a previous stage because that's actually not working for our environment? So the purpose is to provide a framework. We have a number of life cycle stages we're going to progress through, and the decision gates are our mechanism for controlling the flow and the transition through the life cycle stages. So all systems have a life cycle. So, and no matter how complex or how simple your system you're developing is, they will all have a life cycle. So starts with identification of a need. If you don't have a need for something, why develop the system in the first place? Then we go into the sort of development, production, utilization, and then disposal at the end. The role of the system engineer is to tailor this life cycle, including those key decision gates specific to the project. And that's what happens within the project planning process. When we develop that system engineering management plan, that's what we're looking to do to determine, to tailor out of all of these processes and these activities and inputs and outputs, which ones are pertinent or appropriate to the complexity of your system as you're going to develop it. And there's a considerable overhead with system engineering activity. If we were to do every single process and every single activity and every single gate and every single stage, then the cost would be prohibitive. So the tailoring process determines what that element of that is. And quite a famous study by Eric Honor determined that the ideal SE effort over the life cycle cost is only 14%. So then it's a case of finding a balance about the more SE effort we do, the more expensive it's going to be, but the less risk you're going to have implementing that system. So if you do very, very little SE effort, then the risk profile increases significantly, although the cost is less. So it's a double-edged sword. You could cut your corners and do minimal SE effort at less cost, but they end up having to do more rework, which is even more expensive at the end. So it's all about having a balance of SE effort against risk. Three aspects of the life cycle that we need to consider are the business case, the budget, what funding we've got, and the technical viability of that product. At every single decision gate we have within the life cycle, where it's right at the beginning or all the way through architecture, design, verification, validation, every time we have a decision gate, we should be considering the three aspects: the business case, the budget, and the technical product. So that gives us a reference that we can use all the way through, a consistent reference that we're using to assess for making decisions all the way along. So all of you as system engineers will create a technical solution consistent with the business case and the funding. Largely because if you haven't got the money to do it, it will never get delivered anyway. But again, the business budget and technical should be considered and be given equal consideration at decision gate reviews. It's not all about the technical viability. It's not all about the business. It's a balanced view of all of those life cycle aspects at every decision gate as we go through the life cycle. Okay. And this is just a generic, a couple of examples of life cycles for comparison. The one at the top is the ISO 15281 concept right through to retirement stage. And then there's a couple of examples here, a typical high-tech commercial manufacturer. Again, they've just split that life cycle into segments. In this one here, we've got study period, implementation period, and operations period. And then they've subdivided that into various phases rather than the stages. Another example at the bottom, US Department of Energy, project planning, execution, mission, and then split those elements into three on each. So, and typical decision gates: new initiative proposal, concept approval, development approval, production approval. I mean, these are very generic. You will certainly have seen within your projects that you've got a number of decision gates, and it largely depends on the complexity of the system. I've worked in some automotive manufacture where there are dozens and dozens of stage gates relating to various FMEAs, failure mode effective analysis, or FMECAs. And use case approvals and etc. So very generic, but the key thing to take away from this is there should be appropriate levels of decision gates that moderate the execution of that life cycle, so that things don't get missed, things don't get overlooked, and the right level of effort is actually expended on these. Lifecycle approaches, we've got various lifecycle approaches: plan-driven, incremental, iterative, lean, and agile. I'm not going to get into a lot of detail on these. We cover these on the course in quite a lot of detail and the benefits of each one. But the plan-driven was what you might consider for very large teams, multiple companies, very, very procedural, very systematic approach, lots of attention to detail, documentation, requirements, traceability, verification, very systematic, and largely often done when you've got a very complex system or a system of systems being developed with multiple stakeholders. Incremental and iterative, much more flexible. It's quite often used where the stakeholder requirements aren't very well defined. And I hear you say, are the stakeholder requirements ever well defined? But if you don't have very clear stakeholder requirements, then it gives you an opportunity to do some rapid prototyping, put that in front of the stakeholder and say, is this what you're looking for? Yes, no, slightly. And then we can go back and we can iterate over that to define and refine the requirements to meet the stakeholders' needs. So that incremental iterative, generally used for smaller, less complex systems, very flexible, and provides a lot of velocity and adaptability over the very rigid plan-driven approach I mentioned earlier. So, quite often, the customer or stakeholder can be incorporated within the project team to provide continual feedback, and that's almost a bit like Agile, where you've got everybody working on the same environment. So incremental and iterative. So we've got about 10 minutes or so left before questions. So going to touch on requirements and the introduction to requirements and what the requirements actually provide us, and as I mentioned earlier, the whole requirements definition process and capture and recording and traceability is fundamentally important to a system. If you can't capture requirements properly and manage those requirements properly, then your system development is almost certainly doomed from the beginning, I would say. So correctly defined requirements provide clarity, precision, and avoidance of ambiguity. I quite often use the word 3 C's: clear, concise, and correct. There are a whole load of other parameters, but clear, concise, and correct. So we want the requirements to be very clear. The clearer the requirements are, the more we can avoid ambiguity. If there is a opportunity to misinterpret a requirement or interpret it in multiple ways, you can bet your bottom dollar it will be interpreted in different ways, and that can have big impact on the supply chain, on the development of the product. Generally, requirements provided in textual format, though they can be driven very often from use case modeling and use case diagrams, which can help us to elicit those requirements and identify the functions required from the system in a pictorial way that then flows through into requirements. So not only the basis of definition, they obviously drive the architectural design, they drive the integration, they drive the verification, drive the validation. So really the fundamental building blocks of every system. So each requirement carries a cost. So again, like anything else, we need to have a balanced approach to capturing requirements, generating requirements, and making sure you've got a sufficient level of requirements to correctly specify the system without going overboard. And you have to know when requirements engineers need to know actually when to stop tweaking, when to stop refining, when to stop fiddling, if you like. If the requirement defines what the system needs to provide and needs to produce or support, then that's what we need to do. So really important to get them defined earlier. The earlier we can do it, the better. And model-based system engineering and SysML can help us drive and define our requirements early in the life cycle. And what we often call left shifting, getting those requirements defined as early as possible in the life cycle so that you can minimize rework later on. So any changes you make later in the life cycle can actually have a significant cost impact because you might need to have to go back and rework multiple stages. So requirements. Different requirements have a different impact on different levels of people within your organization. So the sort of things we're looking for as a practitioner. So if you're there writing requirements and you're defining the requirements and creating traceability, really important that you've got a scalable common repository, something where that requirements can be managed correctly. You need to have some visible context to see how those requirements relate to each other. And you need to be able to handle complexity. And break down complexity into manageable chunks, if you like. So middle managers. So they're more interested in making sure you can reuse those, cut the costs, reuse requirements as much as possible, making sure that you've got traceability between requirements. So that satisfied relationship between lower level and upper level requirements, that validated by traceability to test cases, test scripts, and that verified relationship as well. So. And middle managers may also be interested or concerned in who's got access to that. Have they got what role people have, and should they have access to particular views and particular sets of requirements? And the executive level, the people at the top of the tree, they're more interested in making sure that you can ensure regulatory and contractual compliance. Because if you can't do that, you're going to end up in court getting sued probably for having not being compliant. And we're looking at conformance to standards like SPICE, ASPICE in the automotive industry, CMMI, and delivering to cost and schedules. So that's the sort of focus for requirements and practice at different levels of your organization. Common aspirations, though. Right across the organization, you want to improve productivity. You want to reduce rework as much as possible, because rework is really really expensive, and you want to keep the customer happy. At the end of the day, we all want to have happy customers, and ultimately the executives want to meet business goals. They want to make sure they can produce the product, they can get the system, they can get it to market, they can get it in operation, and pay the bills effectively. So requirements analysis, how do we go about it? It is an iterative activity, as I mentioned earlier. So very, very rarely you'll start off just with a stakeholder requirements and then flow them into system requirements in architectural design. You tend to find as you're going through that process, you're going to iterate over them. You may well have other stakeholders come in, maybe a safety engineer will get involved, or a hazard engineer, or a producibility engineer will come in. And they will, you've not considered this. You need to go back and rework those requirements. So we need to capture them, we define them, we iterate over those requirements, and then we analyze them to make sure there's no deficiencies and what the cost impact is in those requirements. And ultimately review with the customer to establish a baseline. And fundamental that we do baseline requirements, lock them down, save all the history away, and then before we move on to the next stage, so that there's a handover between, say, stakeholder requirements and system requirements. You don't want someone beavering away on system requirements when the stakeholder requirements have not been baselined. So it's a decision gate mechanism, if you like. So when we're defining requirements, we want to consider quantity, quality. So if we can establish the quantity or make that requirement measurable, that makes it much easier to verify. We need to consider how have we got requirements coverage. So things like gap analysis between system requirements and stakeholder requirements, or even the other way around, where we've got loads of system requirements that don't have stakeholder requirements. We're gold plating, if you like. So we need to establish what the coverage of the requirements for the project lifecycle. Timeliness, availability, all of those parameters or categories are important to when writing requirements and capturing and eliciting those requirements. So the output of all this will be a technical description meeting the stakeholder requirements, and I keep iterating it. Need to meet the stakeholder requirements, and there could often be there's multiple stakeholders as well. So it's making sure everyone is happy. Not a specific solution. Certainly at stakeholder and system requirements, it should be absolutely design agnostic. We should not be specifying which product or which component or which manufacturer we're using, because that leads to obsolescence, etc., and constrains the design process. So we'll have system requirements, we'll have performance requirements, functional requirements, which consider what the system shall do, but also non-functional requirements. And people sometimes tend to forget the non-functional ones, the ilities, reliability, availability, security, the training requirements. They are all as important as the functional ones, but we need to make sure that we're capturing those as well and implementing those as we go through. And any constraints on the requirements, they may be lifecycle constraints. So it might be lifecycle constraints, they might be budget constraints. So considering what the constraints are when we define our system requirements. So finally, we will have a baseline set of requirements, which are hopefully complete, non-ambiguous, required in the requirements database. So very important that we're using a appropriate requirements database of some sort, whether it be IBM or Polarian or JAMA or lots of tools out there. You cannot use Word and Excel to manage requirements appropriately across a system engineering project. Should be accessible to all authorized parties and document and released within the system specification. Some characteristics of requirement statements. Necessary. Well, we don't want to have requirements that are not necessary. As I said, should be implementation independent, design agnostic. Unambiguous, the biggest one. If you can interpret it in multiple ways, you can be sure that someone will interpret it in different ways. It should be a complete set. There should be single requirements. And I've seen some hideous requirements in my time where you've got enumerations and multiple sentences in one paragraph of requirements. So need to be single statement. The system shall do X, the system shall do Y. So they need to be technically and budgetally feasible. So no point putting a requirement in the vehicle shall accelerate from 0 to 200 miles an hour in 2 seconds, because it's just not going to happen. It's not feasible. And you need to be consistent. So consistent in terminology, consistent in structure, consistent in language. So if you've got if you're writing requirements in a consistent way, then that means from within different departments or different teams within your organization, you're going to do requirements in a much more consistent way. Requirement should be bounded. So it should be maybe an upper level or a lower level. So it also helps for to make it verifiable. And it should be correct in legal statements. And as we touched on, the executive responsibility should be conforming to any external or regulation legal standards that your organization may be delivering against, maybe automotive, aerospace, safety critical systems, etc. So these are all characteristics from ISO standard 29148, which you may or may not be familiar with. So these are the key characteristics you want to be looking for when you're writing requirements. So the course over the 2 days also includes lessons on verification, on validation. We talk about test cases and test plans. We also have a session on configuration and change management, as I touched on at the beginning, about configuration change control boards, audit histories, configuration change management processes as well. And what we've also incorporated over the last year, we used to have a separate requirements writing course. In fact, we still do have a separate requirements writing course, a 1-day course. We've incorporated that into the system engineering, introduction to system engineering course. So we have a really good workshop, and this is very popular. We have a group workshop where we split into groups, and then we develop following the requirements writing lessons, we develop some stakeholder requirements, we drive some system requirements, we work on some verification criteria against those, and that tends to work really well. And we can do that based on some, if you want to do this in your organization on site, we can actually tailor that to a typical system you may be developing, or quite generally we can use a coffee maker or a vacuum cleaner or something, as a means to do that. So that's we do that on the second day, and we spend as long as we actually as we need on that. I think it's a really valuable way of actually putting the lessons into practice and having some physical opportunity to actually write some requirements and get some direct feedback on them. So that's what we do for the rest of the course. Just as a reminder, we do have remaining dates, our public training dates in July and October, with the requirements writing included. We are offering anybody on this webinar and this call a 10% discount if you want to book on those. And we also offer an additional 10% discount if you have multiple delegates attending one of our courses. So please feel free to contact us. There's further information on this. We'll send out this slide pack afterwards, Sarah, I think, and contact us, reach out. SyntheSys Technologies Training. Our email address is cet@synthesys.co.uk, and I really hope to be meeting some of you in person over the next few months. So was there some questions to address, Sarah?
Yeah, I think Gordon had asked, what if the stakeholders cannot identify what they want, but can only say what they don't want? This means that you cannot start off with a stakeholder set of requirements. Have you got any thoughts on that, Mark?
Yeah, that's where the incremental and iterative comes in. Instead of using the plan-driven, sequential, heavy, systematic view, the incremental and iterative approach allows you to do some immediate initial prototyping, some initial concepts, present that to the stakeholder and say, yeah, are we getting close, or do we need to go back and revise it? So I've done this in the past myself, where we've actually done a mock-up, and we got the operator, the stakeholder in, and says, oh yeah, actually that's pretty much what I was looking for, but can we have it in green instead of blue? So it's an iterative process, and I would recommend, if stakeholder requirements are not well defined, then that iterative process needs to be done. And there's a lot of soft systems skills around that as well, using workshops and roundtables and techniques like that to actually to establish what the requirements are. Was there any more, Sarah?
Just that one from Gordon.
Thanks, Gordon. Yeah. Okay, so if there's no more questions, I think we're pretty much done. Hopefully that was a good introduction. A little bit rushed perhaps, but we're trying to cram the key elements of the 2-day course into an hour. So hopefully that's given you all a taster of what we cover and how we cover it. And as I said, we can do this either on public courses at our Lincoln University facility. We're using Lincoln University think tank as our public facility at the moment for training. And as I said earlier, if you've got a quorum of people trying to minimize transport in your organization, we can do that on site. And I actually end up doing more on site customer sites than I actually do public ones, because that tends to work quite well. But the option is there for you all. Yes, Gordon, I saw your question. We're doing a similar thing this afternoon for the CSEP preparation. Okay. Well, thank you for your time, everyone. Hope to see you all soon, and we'll send out the a PDF of the slide pack to you after the call.
Thanks, Mark.
Thanks, Mark.
Sarah.
Thank you.
Thank you. Bye-bye. Bye.
Thanks,
Bye.
everyone.